Alright guys, we're going to talk about how you show two triangles similar. Again, these are more proof format, but it's good practice in the long run. So we'll start off with 3 examples. This should all be review. Go ahead and in your Google Classroom comments for these notes, answer A, B, and C of got it, kind of got it, or no clue, just for my information and to show that you listened to the notes and went through some of the notes. Okay? So let's go ahead and start this. In example A, as a review, we're going to factor out the GCF. So we want to look at the biggest number that can divide 4, 6, and 18, and that number is going to be 2. So 2 is my GCF. Then we also, before we move on, we want to check, does my GCF include a variable? How do I know it does? Because all the terms have the same letter, same variable. So I pick the lower one, which is x. So my actual GCF is going to be 2x, and then I do the dividing. 4 divided by 2, that gives me 2. X to the third divided by x, we're left with 2 x's. Negative 6 divided by 2, negative 3, and that left with 1x. 18 divided by 2, that's positive 9, and I'm left with no x's. And your GCF always goes out in front. Alright, so that's it. For example B, complete the extended ratio. There's 2 options to do the extended ratio. I'm going to do the faster one. So if you look, I want to compare the top extended ratio with the bottom. And I'm looking for 2 numbers that are actually in both matching spots. So if you look, 1 and 12, these are actually 2 numbers. And the question I want to ask myself is, what do I multiply 1 by to get to 12? So 1 times what gives me 12? And that answer is, I have to multiply by 12. So what I'm going to do is do the same for all these. Multiply by 12. If I multiply the second guy by 12, it's actually 12 square root of 3. Again, I cannot multiply with the 3 because it's under the square root, so I just write it as a multiplication problem. And then here, I'm going to do the same thing. These are proportions. What you do to one, you do to all of them. So it's times 12. 2 times 12, that gives me 24. And we have now filled in the extended ratio. Last but not least, we're going to solve the proportion by cross multiplying. So I like to multiply with the x's first. That's going to give me 2x to the second. Multiply here, that gives me equal to 50. Solve for x, I need to divide by 2 first. X squared equals 25. And now to solve for x, I have to get rid of the power of 2. To get rid of the power of 2, I square root both sides. So the square root this side, square root this side, square root, power of 2 cancel out. I'm left with x equals, the square root of 25 is actually plus minus 5. Alright, let's move on. Okay, so real quick review. Again, we've been pounding this hopefully so much that you get it already. Anytime you have similar figures, there's 2 facts we have to know. And first fact is angles are congruent as long as they are corresponding, matching. Okay, so I'm going to put that in, corresponding. Angles are congruent. Alright, the second fact we know is sides are proportional. Again, that's corresponding sides. So the sides have to match before we can create equal fractions. Alright, so let's use this information for example D. And in example D, we want to find the scale factor. Again, scale factor deals with the sides. And we have a scale factor because we know these 2 triangles are similar. So to find the scale factor, we in essence just want to find what I like to call the main ratio or fraction. Fraction and ratio mean the same thing. So what we're going to do to find the scale factor is we're going to match sides that can actually create a fraction without any variables. So let's see what fractions we can create with matching sides. So right now it might be hard to see which sides match with each other, but I'm going to use the statement up here to figure it out. So let's start with LM. LM is the first two letters here. So I want to see the first two letters in the second statement, which is PQ. So LM, based on the statement above, matches with PQ. If you notice, that's not a good two sides to find the scale factor because I don't know what PQ is. So let's choose a different set of sides. So let's go with MQ. Let's see who MQ matches with. So again, let's use our statement here. Sorry, MO. MO matches with QR. So let's look. MO and QR match. Again, this is not going to be helpful because I don't know what QR is. So my last option is going to be LO. So let's look at our statement. And it's kind of obvious who LO matches with, but let's just double check. LO matches with PR. So I can use those two sides for my scale factor. So I'm going to go for my scale factor. I'm going to use LO over PR. And I'm going to put the numbers for their measures. So LO has a measure of 18. PR has a measure of 27. And I want to reduce if possible, which in this case we can reduce by 9. So if I reduce by 9, which means divide by 9 to both the top and bottom, 18 divided by 9 gives me 2. 27 divided by 9 gives me 3. 2/3 is now my scale factor. Okay? And this, because 2/3 is less than 1, this would be a reduction. Remember, less than 1 scale factor is reduction. Anything bigger than 1 is an enlargement. All right, let's move on to example E. Again, what you'll notice is it says the two triangles are similar. Set up a proportion, but do not solve for x. So to help me out, I like to redraw these triangles. So I have the little triangle, and then I'm going to have the bigger triangle. Okay? So I know we don't have letters in there, but we're going to match up the measurements. So this 6 from here to here will be here. Okay? Let's color code this to make it a little easier. So this is there. All right. This bottom, we'll do green, is this bottom here. And that's going to be x minus 1. Okay, that bottom matches with this bottom here, which is 2x plus 4. Cool. Now we have 6 has to match with this side, and we actually do know the measure. We'll put it in purple. it be from here all the way to here. So we want to know that measurement. So if you think about it, from here to here, the blue is 6, but we're also adding in x. So it's going to be 6 plus whatever x is. So this is going to be 6 plus x. I want you to think of this as, imagine if x, let's pretend x was a number. Let's say x was 5. So we'll put 5 here. How would you get this entire measurement? You would simply just add these two and you would get 11. But x, we don't know what it is, but we can treat it as if it was a number, which means we would just add these two numbers together, 6 plus x. All right? So now we want to create the proportion, but we're not going to solve for x. So we want to solve for x, so let's create a proportion. So we're just going to match some sides together. We already know they're similar, so it's very easy when you separate them. X minus 1 is going to match with 2x plus 4, so they are going to go in their own fraction. So x minus 1 over 2x plus 4 equals, and now we're going to match two other sides. So I did small side over big side. So my new fraction has to be small triangle over big triangle. So it's going to be 6 over 6 plus x. Okay, and that's all we're doing for example E. We're not solving. We'll talk about solving later. All right, let's move on to F. Okay, so this is a proof. We're going to go through it. I'll explain as best I can using this bank of reasons. They give us our statements. All right, so anytime we have a statement, I'm going to put the reason, and that statement I want to put into the drawing with symbols. Our goal is to prove these two triangles similar. So before I even start, anytime you have overlapping triangles, I like to draw them separately. Okay, so let's draw these guys separately. So we have ABE, and then we have the bigger triangle. And that's going to be ACD. When you draw them separately, it's a little easier to start matching some sides and angles together. All right, so let's go to our given. Here, a given, proof. Our first statement is our given. BE is parallel to CD. So the bank of reasons, should be pretty simple. This is given. I'm going to put that into both of my drawings. So we'll do it in red. BE is parallel to CD. I'll do it here just for reference. Okay, again, these little arrows I'm putting in mean parallel. So we're good there. Just remember, when you see parallel as a given, you want to start thinking like corresponding angles, interior angles, consecutive exterior angles, all those postulates, all right? So now let's look at our next statement. Our next statement says angle ABE is congruent to angle ACD. So ABE, I'm going to go ahead and label these into each drawing. So ABE, so this angle here, ABE is congruent to ACD, ACD. All right? That was one of the statements. Now we have to figure out why. So if you look, remember I told you, anytime you have parallel, you should start thinking all the stuff that comes with parallel lines. All right? To help you see this, we're going to go to our original drawing, and I'm going to ignore this or erase this line so you can see it a little bit better. And I'm going to redraw this a little more clear. So if you look, this is my parallel line, this is my parallel line, and this guy is my transversal. If you notice, when I make the drawing like this, these angles are corresponding. Okay? This is one of the postulates we got to be able to see. They match, they correspond. When you have parallel lines and a transversal, corresponding angles are always congruent. Okay? So, there's my reason. Corresponding angles are congruent. So, my reason is corresponding angles. Okay? So now I have, if you look, an angle, angle. If I have one more angle, we can then use angle, angle. So what we want to do is see if I can figure out an angle from here to be congruent to an angle from here. If you look, we're going to look at angle A. And the reason angle A is important because they are the same angle. When you have overlapping figures like this, they will have the same angle. In this case, angle A. Angle A, when you separate them, is a little bit easier to see. This angle A is exactly this angle A. I can now say these two angles, even though they're the same, we treat them as separate angles, but because they are the same, we can say they are congruent. Anytime you have overlapping angles, that's called reflexive property of congruent angles. Okay? So now if you look, looking at our separated drawings, I now have enough information for the shortcut. I got two sets of angles. I got the purple angles congruent, I got the blue angles congruent. I can now say that these two triangles are similar, and the shortcut I'm using is going to be angle, angle similarity. All right. One more example. We are going to assume these two triangles are similar. We're going to find the height. All we got to do is set up proportions. So we're going to figure out two fractions. One involves the height, or in this case it's labeled my x. So my first one, I want to put my x in there. Who does x match with? It matches with 5. And then again, I went from the tree drawing for the top, so tree over guy, tree over man. So I'm going to take another measurement from the tree, which in this case I'm going to choose 14, and match it with the man drawing 7. We are going to cross multiply and solve. So 7x is going to equal 70. Divide both sides by 7. X equals 10. So the height of the tree is 10.